So good evening, everyone. My name is Sameer, and today I'm going to talk about kind of like an entire life cycle of a query execution in Spark SQL. More specifically, I would like to focus on two key things. First of all, I'd focus on Catalyst, which is Spark SQL's front-end execution engine. And then I'll talk a little bit about Project Tungsten, or the Tungsten execution engine, which comprises of Spark SQL's backend. So just a brief background about me. I'm Sameer. I'm a software engineer at Databricks, where I primarily work on Spark Core and Spark SQL. I received my PhD in databases from UC Berkeley AMP Lab back in 2014, where my research primarily focused on BlinkDB, which is an approximate query processing framework that was built on top of Spark. So let me start off this talk with a little bit of background. What exactly is going underneath the covers when you create an RDD in Spark? So from a high level, an RDD really encodes three things. First of all, it encodes the kind of dependencies that's basically used to construct that RDD. An RDD might be constructed from a text file, or it might be constructed from a list of other RDDs using some operations. So this is what it encodes. Second, it encodes how you partition data, or more specifically, how you partition compute such that you can actually operate on this RDD in a distributed fashion. And finally, it encodes some kind of a compute function, which is a mapping between every partition to an iterator of data that's actually stored within that RDD. So all in all, this is essentially the interface or API that RDD provides. And this simple API is actually powerful enough to support a wide range of libraries on top of Spark. In fact, every major library that you hear about, Spark SQL, data frames, data sets, Spark streaming, all of these actually are built on this simple RDD API. But what's wrong about this API from a programmer's perspective? So if you look at the compute function, this compute function is actually pretty opaque to Spark. What I mean by opacity here is that if I have a function that's actually maybe like joining two tables, or maybe it's trying to filter some data set or prune some columns, Spark knows very little about what the user intent is. And as a result, it actually minimizes or limits the scope of optimizations that Spark can automatically do. Second, if we look at this data also is pretty opaque. And what this means is that since we do not really know what kind of data Spark is trying to operate on, we can't really prune out data that's unnecessary for the query that you operate on. And finally, even though this programming model is pretty powerful, from a user perspective, it's actually extremely verbose and sometimes very hard to understand. For example, here is a simple query in RDD land, or using the RDD API, and all it's trying to do is basically something like this. So it's trying to basically just select a department with an average age and doing a group by. It's very much understandable in SQL land, or maybe in data frame API land, in which you can actually just write these queries from a user perspective. But it's extremely hard and verbose to write and understand in an RDD land. Now, this should not really come as a surprise, especially to people who are familiar with the database programming model, or more specifically, some kind of a SQL or structured programming model, because this kind of programming model actually gives us two things that are really important in executing these kind of queries. First of all, this programming model actually gives us some kind of high-level APIs. So you can actually write queries in SQL, or just like using data frames or data sets, and these APIs allow us to write programs that describe what data operations are needed, instead of actually specifying how to execute these operations. And second, since these data models or data sets can now actually, since these data sets and data models are more transparent, the optimizer, or more specifically the engine, actually knows about what it's processing and how it's processing it. As a result of it, it's able to optimize these query plans in a much, much deeper fashion. So with this in mind, here is what the Spark SQL end-to-end pipeline looks like. A user writes a query. It could either be in SQL, it could be a data frame, or it could be a data set. And this essentially gets converted into a query plan. A query plan is nothing but an abstraction of the user's program. And it could also be called a tree. And what Catalyst, which is the front-end part of Spark SQL, essentially does is that it applies a series of transformations. And I'll talk a little bit more about what a tree and transformations are in the next part of the talk. But what it really does is that it takes a tree like this, and then applies a series of transformation to optimize that tree or to optimize that plan. So once we get this plan, Spark then figures out or generates code to execute this query. Or more specifically, it actually converts it into a DAG of RDDs, which then gets executed on a cluster. And this essentially is the job of the Tungsten execution engine. So again, my talk would basically give introduction of both these parts. We'll first talk about Catalyst, which is responsible for figuring out what the query plan is, and then we'll talk about how these transformations optimize your query plan. And once we get an optimized query plan, we'll delve a little bit into Project Tungsten, which essentially converts a query plan into a DAG of RDDs. So let's look into how Catalyst works, or how the front end of the Spark SQL execution engine works. So let's start with trees, or the abstraction of these user programs. So let me demonstrate what trees are using a very simple example query. So here we have a query that's essentially joining two tables, T1 and T2. It's trying to filter on some attributes. So for example, in this case, it's trying to see that the ID column of both the tables is the same. And then it also filters on the fact that the ID column of the second table is greater than 50 multiplied by 1,000. From that, it selects a bunch of rows and expressions. So in this case, it's selecting the ID column of the first table, tries to select 1 plus 2 plus T1 dot value, and finally it computes an aggregate over one of these things it selected. So now let's actually look at these things that are highlighted here. What these are basically expressions in Spark SQL land. An expression basically represents a new value that's computed based on the input values. So things like sum of v, which is computed from v, is an expression. Similarly, 1 plus 2 plus T1 dot value, which is being computed from T1 dot value, is an expression. So all in all, first of all, we try to find out the kind of expressions your query has. Now, an expression, practically speaking, is just a way of looking at input columns and trying to generate new columns from that query. Now, once we have that, once we have these sets of, or once we have identified these sets of expressions or attributes, the next step is to actually figure out a query plan. Now, a query plan is basically, or the way we figure out a query plan is that we figure out these kind of data operations. So this data operation could be of the type select, join, filters, and things like that. We try to figure out these kind of data operations and then map it to these query plan or logical plan nodes. So these logical plan nodes in this specific case, for example, could be a scan operator that's scanning the entire tables T1 and T2. It's then joining it, maybe filtering it, projecting it, and aggregating it. So all in all, we got two things. We identified the expressions, and then we also identified a query plan to encode or execute this query. Now this essentially, a query plan that essentially in some ways is the blueprint of query execution, can be of two types. One, we can have a logical plan. And a logical plan actually describes computation on data sets without really defining how to conduct that computation. So in this specific case, depending on the format of the table, the scan operator implementation might look very different. But as far as the logical plan is concerned, it just logically talks about this operation as being a scan. Similarly, the join implementation could be very different depending on the sizes of these tables or the distribution of the data sets. But the logical plan only concerns about joins, filters, projects, and aggregates. Once we have a logical plan that's set, and we have optimized that plan to our satisfaction, then we convert this into a physical plan. Now, the physical plan, as contrary to the logical plan, describes the computation on data sets with specific definitions on how to compute that, or how to conduct that computation. In this specific case, if I have two tables, T1 and T2, one of these tables might be a Parquet table, the other table might be a JSON table. Depending on the size of the table, maybe you figure out the join implementation has to be a sort merge join. We have some kind of like an aggregate operator. In this case, it might be just a hash aggregate. So this physical plan is another example of a tree that actually encodes how you execute this corresponding plan on a physical machine. So this was basically an example of trees or plans. So again, like we started off with a representation of these plans. We identified expressions. We identified some kind of a query plan. And we tried to basically work with these plans. We tried looking at the logical plan and a physical plan. Now, what do we do with a plan? The next step with the plan, or how we process these plans, is by applying some kind of transformations on these plans. Now, let me give an example of what a transformation is. So from a high level, transformation is nothing but a function that's associated with every tree, and it's used to implement a single rule. If we look at a simple expression that we just saw earlier, there was an expression that was trying to calculate 1 plus 2 plus t1 dot value. So the expression tree of this expression looks something like this. So the way to read this tree would be from bottom to top. So we have 1 and 2, which are two literal types at the bottom. They are being added. So we have an add expression node here. And then they are being added again with an attribute t1 dot value. So we have expression trees like this. Now a simple transformation or a simple rule could basically prevent you from computing 1 plus 2 every time you see a new t1 dot value. Right? Pretty simple. You would want to avoid these type of log costs and runtime and rather just convert this into 3 plus t1 dot value right at compile time. So in order to basically do this, we have a transformation, or we can actually define a transformation. This is called constant folding, which can evaluate things like 1 plus 2 just once at compile time and convert it into expression trees like this. In this specific case, it is just add a literal 3 and t1 dot value. Now, how do we do this? The way we do this is that Spark SQL or Catalyst basically defines a transform as a partial function. Now, partial functions in Scala are just functions that's basically defined for a subset of its possible arguments. So let me demonstrate this with an example. Let's say we have an expression. We can define a partial function that matches this add expression, and it says that if I have an add expression with two literals, then you convert that into a new literal of x plus y, right? So again, if you think about it, what we are trying to do is we are trying to convert everything of the form 1 plus 2, or add 1 comma 2, to something like 3, right? So in this case, like transformations in Spark SQL land is just basically things like partial function that can add or that can actually specify these kind of rules. So if we apply this transformation on this expression tree that we saw earlier, we first go to the first node. And in this specific case, we see that the add node here has a left child that's another add node. So this partial function does not actually match this node. We then go to the node below, and we see that this partial function should now match this kind of expression tree, which is add and two literals at the bottom. So again, like what this really does is that it can actually convert everything like this into a new literal of 3. So pretty simple, right? But these these kind of transformations combined can actually result in pretty powerful and pretty optimized plans. So just an example of another kind of like really famous optimization or transformation is that of predicate pushdown. So what predicate pushdown is that if your query actually has a lot of filters, you would want to push these filters as close to the data source as possible, because you don't want like your data to be like transferred in the query plan all over the place. So what this predicate pushdown transformation does is that it just simply matches for all filter operators. It tries to figure out if it's trying to filter some column. So for example, in this case, the filter operator was trying to figure out something like t2.id to be greater than 50,000. The output of the join does not actually affect that filter. So you can actually push that part of the filter just above the scan operator. Similarly, the condition t1.id equal to t2.id can actually pushed inside the join. So all in all, you can actually have these kind of transformations, again, applied to your tree or query plan in order to optimize these query plans. Another example of this transformation, as we just saw, was constant folding. So again, like in this specific case, you could figure out that 1 plus 2 could be just folded into a single constant, which is 3. And t2.id greater than 50 into 1,000 could just be evaluated as 50,000. So this is another example of such a transformation. Another example could be just column pruning. So normally, if you're reading a lot of data, you have like a lot of columns which might not be necessary for the query to evaluate. So you can actually inject these project operators, which can prune out all the unnecessary columns and only have columns that you are interested in. So these are just simple examples of like some transformations that can operate on the query plan. And what they do is that what Catalyst does is it basically applies these kind of transformations one after the other. And if you look at the Catalyst code base, we have like a large number of these transformations added by people like in the community. And what this really does is it basically can optimize your query plan into a more optimal version that can execute the same query. So we talked about two things in Catalyst. We talked about trees, which was some kind of an abstraction of the user program. And then we also talked about transformations, which was able to transform one tree to the other. And the goal of this was to basically have like more optimal query plans. Now let me actually give a brief introduction of what Tungsten does. So once you have a query plan, the next step is to actually convert that query plan into a DAG of RDDs, or basically convert it into code that would now be executed on the cluster. So how do we actually convert this into code? So again, let's look at a simple query. This query is simply counting the number of rows in store sales where the value of this attribute, SS item SK, is equal to 1,000. So if we again look at the query plan, it might be just as simple as scanning the data, trying to filter some value, projecting it, pruning out all the unnecessary columns because we don't need it, and then finally aggregating the count. So the way traditional databases normally execute these kind of queries was by using this Volcano iterator model. And what this Volcano iterator model is that it has been essentially a standard in database community for almost like 30 years. And this model essentially says that each operator has to implement an iterator interface that essentially consumes record from its input operator or the operator below it, and then optionally output any record to the operator that's basically after that in its chain. So just a brief example of how this would look for a filter operator that we just saw in this thing. So if you look at the filter operator, a iterator interface or this filter operator model would basically look like this. So we have a .next, which is being defined by the filter operator. And the logic in .next basically evaluates this current predicate or whatever the filter is trying to filter on, and then optionally returns this corresponding row. Right? And in this process, it's trying to read or the value of its child, and then it returns that. So now, I mean, this Volcano iterator model has like a bunch of things that are really nice about it. First of all, this is extremely simple to reason about and implement. If I have to add a new operator in my database, all I have to do is to basically just implement an iterator interface and not worry about how this operator interacts with any of the existing operators that my database has. Second, it gives us composability. So what this means is that when I am implementing a filter operator, I don't have to worry about how it composes with with projects, or how it composes with scans underneath it. But on the other hand, the Volcano iterator model also is pretty inefficient. And this really is the downside of the Volcano iterator model. So there are really three key things that are bad, so as to say, for Volcano iterator model. First, there are just too many virtual function calls. Since each operator is actually agnostic, essentially if I'm processing code in one of the operators, I'm really agnostic to the operator below me. At runtime, it's all dynamic dispatching. Second, each operator essentially exposes an iterator interface. So that means that the operator below it has to write its row or any intermediate data representation in either the memory or the cache, and the other operator has to read it. What this means is now your main memory or your cache quickly becomes the bottleneck. And finally, this kind of code in general is extremely hard for computers or chips to understand. And it cannot really take advantage of a lot of modern hardware features, like SIMD, pipelining, branch prediction, and things like that. So on the contrary, what Spark SQL does is that it tries to actually generate code that maps one-to-one with the code that we are trying to, or with the query that we are trying to run. And this is essentially the high-level idea behind whole-state code generation. So what this means is that instead of actually generating iterator code for each of these following operators, what we try to generate in an ideal case is something like this. So as you can see, the scan operator roughly corresponds to the for loop, or something that iterates over all these rows. The if condition roughly corresponds to the filter condition, which is just basically filtering on these on the attribute. And the aggregate is nothing but the count. Now, if we just look at this code, first of all, it's extremely simple as just compared to the filter operator code that we saw. And going back to the downsides of the Volcano iterator model, if you look at the first one, The code that I just showed you has no virtual function calls. The second case, it has all the data that's basically being stored in CPU registers. There is just a single count variable that's incremented every time. And finally, this type of code is pretty easy for compilers to understand. So essentially, a lot of modern CPU features like branch prediction, pipelining, prefetching can actually be leveraged in order to speed queries like this. So I didn't actually go into a lot of details about whole state code generation. I actually gave a much deeper dive talk in like a couple of meetups before. But this is a high-level idea of how Spark actually does whole state code generation and generates code that looks like this by looking at your queries. So just to recap, the whole state code generation, the key idea is to fuse together operators so that the generated code actually looks pretty much like hand-optimized code or things that you would write if you would have been implementing your query. And the key idea here is that we first of all identify chains of these operators which can be fused together, and then we compile each of these stage into a single function. So this entire for loop with counts and if statement would have been compiled into a single function. And finally, the goal here is to just get a functionality of a general purpose execution engine. We don't want to be handwriting code or hand optimizing our queries. But we also, at the same time, want performance as if somebody actually sat down and hand wrote all the queries that you ever executed in Spark. So again, like I am skipping over a lot of like technical part of how whole state code generation is done. But from a high level, what Spark leverages is this excellent paper by Thomas Newman that talked about a lot of these vectorization and whole state code generation technique. And we leverage a lot of these techniques in this paper to identify chains of operators that could be fused together, kind of like do partitioning of on the query plan and try to generate code automatically that would execute orders of magnitude faster. So just, I'll kind of like conclude my talk by giving some performance numbers between 2.0 and previous versions of Spark. So 2.0 was the first version of Spark where we enabled whole state code generation and a lot of like these techniques that we talked about in Catalyst. And here are some of the operator benchmarks. So on the left side of the first column, I have various operators in Spark. The left side number, the second column has like Spark 1.6 numbers of cost of processing per row. So these numbers are in nanoseconds. And on the third column, I have the Spark 2.0 numbers. So we see that for things like filters, some with group bys and hash joins and things like that, we see almost 5 to 30 times speedups just by generating these code. Spark 2.0 also had a new radix sort implementation, which resulted in around 10 to 100 times speedup in performance. We did not find much speed up between 1.6 and 2.0 for the sort merge join, because shuffling in this case was still the major bottleneck. And then we also, this I didn't talk about much in my talk, but we also had a new vectorized reader, which ended up speeding performance for the Parquet decoding by almost an order of magnitude. So this is basically the end-to-end result on like the TPC-DES benchmarks between 1.6 and 2.0. On the y-axis, I have the query response time. This benchmark was done on a scale factor of 1500 on 100 cores. And obviously, the smaller bar or lesser query time is actually better. Spark 2.0 is, in general, like around 3 to 5 times faster for a wide majority of queries as compared to 1.6. And this is just, I believe, 39 queries, because Spark 1.6 only supported 39 of these queries, whereas Spark 2.0 actually supports all TPC-DES queries. So what's next? In terms of performance, there are 3 key things that I'm really excited about for Spark 2.2 and beyond. First of all, in newer versions of Spark, the community is actively working on a cost-based optimizer. So the key idea behind a cost-based optimizer is to leverage these kind of table and column level statistics to optimize your joins and aggregates. And as part of this, we already have a basic statistics collection framework in Spark 2.1. And then a full-fledged cost-based optimizer would now be part of Spark 2.0. We are also working on boosting Spark's performance on many core machines. And Shifan Pu, who was one of our interns at Databricks this summer, had an excellent talk about in-memory and single-node shuffle in Spark Summit Europe that just went by. And finally, we are always working on improving the quality of generated code and better integration with the in-memory column format in Spark. So I'll conclude my talk by just giving a pointer about Spark Summit East, which is going to be held in Boston from February 7 to 9. And if you have not already registered, there is a Meetup discount code, Meetup15, which would give you 15% off on the registration cost. And last but not the least, we are hiring. So if you're interested in solving hard technical problems in big data and are excited about working with Apache Spark, please talk to us after the meetup. Thank you.
Any questions for Sameer?
Sure. Couple of questions. One, can you talk about the cost-based optimizer, like what sort of journey enumeration you're going to do?
Right. So there are a couple of things. Like, I mean, the basic statistics collection frameworks can actually like keep track of the cardinality, the number of distinct values, heavy hitters, and these kind of things in your input data sets. And then based on that, we can actually do better. So one of the first things you can do is better like things like broadcast, like whether we should broadcast or not. And then like, I mean, we can also do like better partitioning, better like join estimation, and things like this.
Are you going to do reorder joins?
Yes, so this is another thing that, I mean, this actually enables you. So if you know the cost of each joins, you can actually reorder them so that like your query plan would be much more efficient. The cardinality would help in that case.
And another small thing, can you go to your last catalyst slide where you were talking about rules?
This one?
Yeah.
Yeah.
Can you push the filter on the left side?
Yes, you can. So Spark 2, I actually should have done that. The reason I didn't do that is because, so I'll repeat the question. The question was that if I have a filter on t2.id greater than 50,000, and I already know that t1.id is equal to t2.id, I could have actually pushed a filter on t1.id on the left-hand side of the join, right? It's pretty obvious. So yes, Spark 2.0 actually has a constraint propagation framework that can identify constraints like this, and then automatically infer filters or new filters based on that constraint. I was debating of whether I should include it or not, but maybe I should. Yeah.
And just to complete, when you're comparing 1.6 to 2.0, that was 1.6 with tungsten disabled.
So 1.6 actually did not have whole state code generation. It did have like a bit of optimization. So basically, it had better memory management, which is also came under the purview of like Project Tungsten Phase 1. So the numbers I showed you had those kind of optimizations enabled. But I mean, it did not have whole state code generation.
How it applies to the structured streaming?
So structured streaming is also built on top of like the Catalyst and the whole Tungsten pipeline. So essentially, all of these techniques that I talked about would, in theory, apply to any kind of logical plans that are generated using structured streaming APIs as well.
Anybody else?
It was off topic, just only because you were